Let's discuss a finite square well problem. So, this specifically belongs to the course of quantum mechanics, and if your courses are divided into two parts at undergrad level, this will be covered under quantum mechanics 1. So, this is the diagram for a finite square well problem, or also called a particle in a box problem, because of its figure, because of the shape that this figure takes. Now, what we have here is on this vertical axis that I drew with a dotted line, we have the potential V of x that uh, that is surrounding whatever exists inside this box. And it could be a particle, it could be an electron, or any other particle. And we have on the horizontal axis is the position of that particle inside this box, is given on this horizontal x-axis. Now, the what makes this finite square well problem different from an infinite square well problem is that instead of having this potential infinity, we don't have this as such, but what we have is the particle is confined in a box with some potential V naught at both ends. So the potential energy is comparable with the kinetic energy of the particle that exists inside the box. So our problem is to solve the Schrodinger equation for the energy eigenvalues and the energy eigenstates for such a problem. So we are going to start with looking at this figure and writing down the potential energy as a piecewise function. So if we look at this diagram, what you see is that for x is equal to or less than minus a, you have potential energy V naught. So what I can write here is that V of x is V naught whenever x is less than equal to minus a. And then you can see that inside this box, from minus a to a, we have potential energy is basically zero. So I can write it v of x is zero whenever x lies between minus a and a. And then again, when you move further from a, the potential energy is again v naught for x is greater than a. So this is the potential energy for the given problem. And now the next step is to look for the bound state solution, that is for the energies that are below the potential V naught. Now, energies above V naught will correspond to unbounded states. Uh, I'll just write it down here. So, whenever you have um, energy, let's say E is below V naught, that represents the bound state, while when you have energy E which is greater than V naught is known as the unbounded or unbound state. Now this energy E can is the energy of whatever particle that you're considering inside this box, right? So now, having this potential energy piecewise function, one can write down the energy eigenvalue equation, which is the Schrodinger equation, which is generally written as H on psi is equal to E psi. This is the eigenvalue equation, also known as the Schrodinger's wave equation. Now, because of the problem that we have, you would have to write this differential equation for two scenarios. One is for whatever is inside the box, and the other is whatever is outside the box. So we'll have two different cases. First, let's write down for inside the box, and what you will have is, uh, if you recall, this Hamiltonian is basically p square by 2m, and there is some potential v of x. That's your total energy of the system. That's what Hamiltonian represents on psi of x is equal to E psi of x, right? Now, this is classical, and to move into quantum, we need to promote these observables into operators. And so we know that for momentum, it's negative iota h bar del. And so upon doing that, we can write this energy eigenvalue equation for inside the box as negative h cut square by 2m partial x squared plus. Now note that inside the box we have potential v of x is this thing, so it's basically 0. So instead of this v of x, I'm going to put 0 because we are discussing the case inside the box. And then you would have psi of x is equal to E times psi of x. And that's for inside the box. So let's call this equation 1. And then I'm also going to write down for outside the box the same energy eigenvalue equation, which will now take the form of negative h cut square by 2m partial x squared plus. Now note that whenever you're outside this box, eh, in both the scenarios your potential is v naught, so you'll only have one equation for outside the box, which would be this thing plus v naught, and then you have your psi of x is equal to E times psi of x. Right. Now I'm just going to call this equation 2. Now from equation 1 and equation 2, if you rearrange this and make it if you rearrange it in a way that you can have partial or the derivative at one side and everything else on the other side, what you will get is your equation 1 becomes partial x squared psi of x is equal to minus 2me over h cut square times psi of x. And this is basically your equation 1. And from equation 2, that would become partial squared x psi of x is equal to you would have E minus v naught psi of x. Right now, I forgot the constants. You would have 2 into 2m divided by h cut square, and then you'd have psi of x. Right now, let's just relabel these constants over here. What I'm going to say is I'm going to label k squared as minus 2 k squared as 2me over h cut square, and I'll call this one I'll call it q squared. So this becomes q squared is 2m over h cut square into v naught minus e, right? So I have basically dissolved this negative sign that comes over here. I've missed it before, so there is a negative sign over here, and I have dissolved it in this way. Right. So now the next step is just to substitute these values for k square and q square in these new forms of equation 1 and equation 2. So equation 1, then again it becomes partial squared x psi of x is equal to minus kappa squared or k squared times psi of x, and the other differential equation becomes partial x squared psi of x is equal to q squared psi of x. Now, this is the set of differential equations that we want to solve. So, how are we going to do that? Is let's, well, the solution for the this equation, this one is the same as the solution for infinite square well. So if you recall that, that was simply in terms of uh, sine kx plus cos kx, where you would have some constants attached to both of these functions. Now, but if I look at this equation, the solution to this is what? Well, from your differential equations, you know that this the solution to this equation is in terms of exponentials, which is psi of x is equal to a e power qx plus b e power minus q times x, right? So, well, the you'd note over here that I have written the real exponential solution instead of the complex one, and that's because constant q over here is, you can see, it's positive. So that's why we have this solution is basically real and not imaginary, right? Okay, so the next thing is that the energy eigenstates now must be constructed by connecting these solutions in the three regions, where this is region 1, this one is region 2, and this is region 3, right? Okay, so now what I can do is I can basically write down the general solution to this problem as a piecewise function, just as I wrote the potential energy function as a piecewise function. So you would have, for x is less than minus a, you would have the outside of the box. So the differential equation would be this one, the q1, and the solution to that is a e power qx plus b e power minus qx, right? And for the region that lies between minus a and a, you have the solution that is identical to the infinite square well. You would have c sine kx plus d cos kx. And again, outside x greater than a, which is the region that is again outside, which is this region 3, you would have the same solution as this one, so with different constants, of course. So let's call it f e power qx plus g e power minus qx. Now, the next step from here is that these solutions must satisfy some boundary conditions, right? So we have found a solution. Now, to match it with this problem over here, we need boundary conditions that match with this specific problem or this figure. So, well, the first boundary condition is that your wave function, which is psi of x, must be continuous. And the next one is that the derivative with respect to position, so partial x of psi of x, must also be continuous. Now, well, the first boundary condition, I label it as 1 and the second as 2. The first boundary condition is even valid if you're discussing the case for an infinite square well, while the second boundary condition is specific to this problem where your potential does not become infinite. And the reason for this is because if you recall or if you have any idea that let me give you this in this manner. If you know that the Lagrangian for a scalar field is something like partial mu psi partial mu psi, well, it's not really this. There is some constant over here. I think that's 1 by 2 or something. And then you have some potential v of x or whatever you have, v basically. So this term, the term that is with the derivative, it's known as the kinetic term. uh, Kinetic term, and it is representing the kinetic energy of the system. And so again, in this case, a partial derivative of psi of x, which is partial x of psi, this would represent the kinetic energy of this system that we are talking about. And well, if you have your potential v of x is infinite at some point, if that is the case, then your partial derivative with respect to x of psi, uh, then this implies that this thing cannot be continuous. And the reason is simply that if this thing were to be continuous, then your kinetic energy would be approaching infinity, and that cannot happen. So this is the reason that this second boundary condition over here is only true for the case of of a finite square well. Okay, so now moving forward, before I apply these 1 and 2 boundary conditions, uh, what I'm going to do is I'm going to look at this. I'm going to look at this diagram basically, and uh, let's simplify our energy eigenstate wave function, right? How am I going to do that is, if you look at the region that is outside the well, the wave function must be decaying, or it should be a decaying exponential. We have already established that it is an exponential function outside the wells, but it should be a decaying exponential. And the reason for that is simply because if the exponential was a growing exponential, then the it would it would actually go all the way to infinity, because of course it would be if it's a growing function, it is tending towards infinity. And if that's the case, then the wave function is not normalized, or the wave function cannot be normalized. Because if you look at this diagram, it is basically obvious that if whenever you're getting closer to a potential, the wave function, the value of the wave function should basically be decreasing, because you're approaching a barrier, and the probability of finding a particle closer to that barrier would be less when it's compared to anywhere between the barrier itself. So that's why we can say that the the exponential for uh, outside or at the walls of the well should be should be a decaying exponential. And if I look at this wave function, then I can say, well, we know that this one is for x is less than minus a. This is for x is between minus a, and this is for x is greater than a. So if I put these values of x in these, this is for outside, this is for inside, and again this is for outside. So if I put these values of x in these expressions for outside the well, well, first I have, let me write them down. Q minus a, right? Because we have, this is minus a, so we'd have e power minus qa plus b times exponential minus multiplied by minus is plus, so you'd have qa. And the second, this one for outside, it becomes f e power qa, because we have a is positive now, so we have plus g e power minus qa. And just now that I talked about the wave function should be a decaying exponential outside the well, that would immediately imply that these constants b and f should go to zero, right? Because these constants b and f are with an exponential that is growing with x, so they have to be, and we just established that it cannot be a growing exponential. So to make that term zero, we need those constants to be zero. So then finally for outside, we are left with uh, a e power minus qx and g e power minus q. Well, it should be a over here, and or you can just put it x for now, but we know that x is going to a. And you'd have here, or let me just write a, and here again I'll also have minus qa. Now another simplification that I'm going to use here is that if I look at this diagram for the finite square well, I can crystal clear see that the potential energy function is symmetric with respect to this origin O, right? So what I can write from this is I can write down the symmetric potential condition, which is that v of x is the same as v of minus x. And this simply then implies that the energy eigenstates psi of x are either symmetric or anti-symmetric, right? Well, if you recall quickly from the infinite square well problem, you have your let me just quickly draw the well. Your well is something like this, and you have infinity, infinity, and you have v on vertical axis, and position x is on your horizontal axis. And we have already established in the lecture on infinite square well that for n equals 1, the energy eigenstate function looks something like this, and for n equals 2, the energy eigenstate function looks something like this. And well, you have so on for n equals 3, 4, and 5. So you can see that this function is symmetric about the origin, while this function is anti-symmetric, and all of the other curves that you would have would be either symmetric or anti-symmetric. So well, this then implies that psi of x should be symmetric or antisymmetric. In other words, symmetric implies that it should be an even function, while antisymmetric implies that it should be an odd wave function. So, with this then in mind, let's move on to solve the two sets of these solutions by imposing the symmetry conditions, right? So with these well, let me just call them simplifications for this outside and this symmetry condition v of x is equal to v of minus x. I can write down well, I can break my solution into two parts, which is first one is even and second one would be odd. So for the even part, I can write my psi of x as what? Well, if you look at this psi of x over here, you see that for x is less than minus a, it is we have already established that b goes to 0, so this term would go to 0. And we have also established for in this case that f equals 0, so this would also go to 0. And so we're left with this thing. And for the even case, we would have for x is uh, less than minus a, it is a times e power qx. And for the region that lies in between minus a and a, if you look at this, you have the sum of sine and cosines, but we're only talking about the even part of the solution. And we know if you look at the graphs for sine and cosines, you can see that the sine function is something like this, and the cosine function is something like this. And uh, that's not what it looks like. It's something like this. And you can see from the graphs that the cosine function is the even function, while sine function is the odd one. So for the even part, we'll only be left with d cos kx, like this. And then finally for x is greater than a, we have this thing. So it's g e power minus qx. So you'd have g e power minus qx. Wonderful. Now, in a similar manner, you can also then write down for the odd part, where everything remains the same except for the part that is inside the well. So you'd have again over here for x is less than minus a, you'd have a e power qx. And for the region that lies in between, that is minus a less than x less than a, you would have the odd. Let me just write even with this psi and odd with this psi. Okay, so for the region that is in between, the odd wave function then becomes the sine function. So you would have c sine kx. And again, for outside on the right hand side of the well, you would have g e power minus qx. Right. Okay, so now let's first take the even part. So for even part, let's apply the boundary conditions for the problem. And if I go back to this diagram that we have, what you can see over here is that uh, on the right side of this wall where you have x equals a, what you can see is from the left hand well, because I said that the function is continuous, so approaching this a from the left hand side and from the right hand side, it should assume the same value. And this comes from your course or your knowledge on calculus. So where you discuss limits and so on, right? So derivatives and all. So then this would imply that the solution that is inside this wall must be the same as the solution that is uh, approaching this wall from the right hand side. And if I look at these well, you have from the right hand side you have this thing, and from the inside you have this thing for the even scenario. So what that means is d cos k. Now we're talking about the wall from the right hand side where x is basically equal to a. So instead of writing x, I put a over here, and this should be equal to the well, this one was from the left hand side of the wall, that is x equals a, and it should be equal to approaching the wall from the right hand side of x equals a, which is this thing over here. So this should be equal to g e power minus qx, and this comes from the boundary condition that psi is continuous. But we also know from the second boundary condition that partial x of psi is continuous. So that would imply that the partial derivative with respect to x in this case, this should also be continuous. So that means that approaching the wall x equals a from the left and the right hand side should assume the same value. So that would mean if I take the derivative of this thing, I'd get minus k d sine ka is equal to minus q g e power minus qa. Now I have two equations, and the well, if you if you recall the symmetry condition, the boundary condition at the left hand side of the wall, x equals minus a over here, would yield the same equations, and that is purely due to the reasons that we have this symmetry of v of x about the origin. So that's why if I pick the right hand side of the wall, that is x equals a over here, I can solve my even, and I mean I can apply the boundary conditions to the even wave function and the odd wave function and do all the calculation. Or I could have picked the left hand side of the wall, that is at x equals minus a, and applied the boundary conditions for psi and get my equations. The equations in both the cases would be the same because of the symmetry of potential. Right. So now moving forward, these we know that we have already seen or established that these yeah, these constants k and q, they contain energy terms, right? So keeping that in mind, uh, we want to find the energy, uh, basically our goal is to find the energy eigenvalues, right? So what I'm going to do is I'm going to uh, let's call this equation, small a, and let's call this equation small b. And with that in mind, if I divide these equations, uh, if I divide equation b by a, what I get is you would have this minus k, um, well, this minus minus cancels, right? So you'd have k, and this d, when divided by this d, it would go away, and you would be left with sine ka divided by cos ka equal to, you'd see that g and g would also go away, uh, just as this d and d would go away. And this thing, exponential factors are also the same, so they would also go away, and you'd be left with q on this side. But we know that sine ka over cos ka is tangent ka, and on the right side you have q. So this over here is one of the equations that you got when you were considering the even part of the wave function. And uh, note that these both of these k and q are your functions of energy. That's why this equation that we have just established over here will basically give you a formula to find the allowed energy levels or the allowed energy states of the system, that is of a finite square well, right? So now what I'm going to do is I'm going to quickly recall my value for k, which was square root 2me over h cut square, and for q it's square root 2m v minus e over h cut square. And I'm going to put these values of k and q in this equation, and upon doing so, what I get is um, square root 2me over h cut square times tangent. Now you had k times a, so let's put the value of k, which is again 2 square root 2me over h cut square, and then you had multiplied with a is equal to q, but q is square root 2mv minus e over h cut square. Now the next step from this is to solve this transcendental equation. This equation, by the way, uh, it's called a transcendental equation, and you can solve this transcendental equation by defining some dimensionless parameter, right? So uh, well, you know, or you should know from calculus that uh, you solve a transcendental equation graphically, and well, there are a number of ways in which you can solve it, and the one of the ways that I'm going to be using over here is known as uh, well defining some dimensionless parameter and then solving the equation. So let's define a dimensionless parameter first. I'm going to call it small z, and I'm going to define it as k times a. Note that when you multiply this k and a, uh, you are defining something that is dimensionless, and that's what we want. So that's why I defined it as k times a, which would just be square root 2me over h cut square times uh, times a. But let's put this a also inside the square root, so I would have a squared, right? Okay, now let's well, you have this ka equals this thing, and if I take the square on both sides, I have ka whole squared is equal to uh, 2me over h cut squared a squared, right? So you will soon figure out why am I doing these steps and defining these expressions in such a way. Everything that I'm doing right now is purely mathematical, and there is well, there is, at the essence of it, there is some physics defined, which you are going to see when I plot the graph for z and the function of z. Well, we are just getting ahead of ourselves right now. Let's completely solve this, and then I'll we'll discuss the graph that we get. Right. Anyways, so just as though we did this for k times a, I'm going to do the same thing for q times a. So we know that q is square root 2m over h cut squared times v minus e. That's our q. And so if I define q times a whole squared, what I get is 2m over h cut squared v minus e times a squared. So I have these two equations for k a whole squared and q a whole squared. Right. Now, what I'm going to do is I'm going to add both of these equations, this one and this one, together. And what I get is ka whole squared plus qa whole squared is equal to, well, if you add these two things, you have 2m over h cut square times a square is constant. So, well, that would survive 2m over h cut squared a squared. And when you add these two, you'd have e minus e would become 0, and you'd be left with plus v. So you'd have v over here, right? And now we can see that the this the variable z, basically what it is doing is it is parameterizing the energy of the uh, state psi, right? Of the energy state. And so what I can do now is I can write this thing as z naught squared. So what what this dimensionless parameter z did was simply just parameterize the energy state. And you can think of this constant that is z naught as it is characterizing the strength of the potential energy of our square well, right? If you look at this expression for z naught, right? Okay, so anyways, what this gives you is mm, well, you can now write uh, qa whole squared is equal to z naught squared minus z squared, right? And this then allows you to write your transcendental equation basically as z. If I go back over here, this was your transcendental equation, this one, and you can well, if I have this, I can multiply a on both sides. Let me just write it down over here again. What your transcendental equation is: k a tan ka is equal to q times a. So I've just multiplied a on both sides of the equation, and now I can write this as z tan z is equal to uh, square root, this qa I get it from here, so which is square root of z naught square minus z square, right? And now this is another equation that we have. Right, so now the left hand side of this equation, which is this one, is well, you can call it a modified trigonometric function, while the right hand side is this term is like a radius, right? Radius r, with a z naught squared is equal to this thing. Now, well, the solutions to this equations are actually given by the points where this circle that is on the right hand side of this equation intersects the functions that are z equals to tan z. That's what this means, right? This equation, it means that when these two things are equal, that's where when you get your solutions of the transcendental equation. And so the functions then can be plotted as a function of the parameter z. So on the x-axis you would have, or the horizontal axis you would have z, and on the vertical axis you would have those functions of z. And the intersection points of these curves, which I'm going to draw in a bit, would be, or the intersection points of those curves would determine the allowed values um, of your z, and hence the allowed energies E, right? So well, well, instead of talking, let's get to drawing, which you would have to excuse me for uh, the drawing that I'm going to do. You have on your horizontal axis you have z, and on the vertical axis you have f of z. And well, now if you if you look at this equation, you have to keep this equation in mind all the time while drawing this graph. You know that z is going to assume values from well, 0, then you would have pi by 2, then you would have pi, then you'd have 3 pi by 2, and well, it would keep going on. So you'd have 2 pi over here, somewhere over here you would have 2 pi, and then you would have 5 pi by 2, and so on, right? So well, first of all, I'm going to draw the circle that is given by this equation, that was square root z naught square minus z square. So this circle is well, it would be something like, well, you'll have to excuse me for this drawing. Okay, it would be something like this, right? And then we have our functions, uh, that would be this tan of z And I'm going to simply first draw the the functions that are for tan of z. Well, you know that tan at 0 is simply 0, but so the graph or the function that you would get on your plot would look something like this for tan of z. Well, let me first draw the asymptote at pi by 2. So it would look something like this, and this is where it intersects. Now, to draw the next curve, I would I should mention something, that everything that we did from this point onwards was for even psi of x. You could do the exact same thing for by taking this odd function for psi of x, and because these are the same in both. The only difference is in this the function that lies between minus a and a, and the difference is simply of the well, for even you have cos, and for odd you have sine, and everything else is the same. So the transcendental equation then for the case of odd would become, let me just write it over here. So for odd, what you would have is the transcendental equation would be z n cot zn, right? So you can do this as an exercise. You all you have to do is follow the exact same steps that we followed from this point onwards, but for the odd wave function, which is this one, right? And so you know that the cotangent at 0 is well, when you do it you get infinity, which means that it does not exist. But the cotangent at pi, uh, at pi by 2, you'd have a line that looks well, let's first draw all these asymptotes very quickly. At pi you would have an asymptote, at 3 pi by 2 you would have an asymptote, and likewise you would have asymptotes at these values of z. And so for this curve is for uh, z z tan of z, while the next curve is, or it would be for it would be for z cot of z. And again then you would have the next one would be again for z tan of z. So this one again is for z tan of z, and so you get the point. The same pattern continues on and on. Now the the point that you should understand from this graph is basically that this circle, this circle that was drawn using this equation, basically it characterizes the potential energy of your well. So the bigger the circle, the bigger the potential energy, and the more the points of intersection you would keep getting on this circle and these curves for tan and cotangent, right? So well, what I'm trying to say is that the intersection of uh, these uh, these curves and this line of circle yields only one state, right? If you consider this one. So no matter how small your potential energy is, you would always have one state. So I could make this extremely small such that it goes to zero, but you'd still have one uh, one energy state, which is n equals zero, right? And the bigger this circle becomes, the more the energy states that you would get. So that means that the number of solutions to the equation in a finite square well depend on the size of z naught. And if you look back at this equation, you know that z naught carries this potential v. So that means that this, as the potential v naught becomes higher and higher and higher, the points or the energy states that you would be getting would be higher and higher and higher. And it also depends on the width of the potential well. In fact, it depends on the square of the width of the potential well. So again, it would become uh, higher and higher and higher, the energy states, as if you increase the width of the potential well. And if you think about it physically, if you look at this diagram, if I increase the width, the distance between minus a and a, if I increase that distance, it is obvious that the particle can have more and more and more states, right? Okay, so well, basically, this is all that you needed to know about the finite square well problem. And I would like to leave you on one remark, that the properties that are quantum mechanical, they have finite probability of being found. So and that is, there is always some finite probability for a particle to be found at some position x, right? However, in a classical scenario where you have classical particles, they may not at exist everywhere. So for example, let me just quickly um, draw a potential energy diagram. So if, for example, you have, uh, let's say this is the total energy E of your particle that it can carry. So that's the total energy of the particle. And you have this energy curve, as let's say it's something like this. Well, um, or let's not just draw it like this. Just give me a second. Okay, so let's instead say that the curve, or the energy curve, it's something like this. And your particle has the total energy E naught. Then what happens is that in a classical picture, you can clearly see that this region that is over here, so this line is forbidden. And the reason for that is because this line is above, or it has energy that is above the total energy E naught of the particle. And so it can never go into this region classically. However, everything that is below this energy E, or at this energy E, is accessible to the particle. So this part, all of this thing is accessible to the particle. So it can move from this point, let's call it x1, to this point x2. And again, over here, this line, it carries more energy than the total energy of the particle, and therefore it cannot access this region. So let's call this region 1, this region 2, and region 3. So region uh, 1 and 3 are not accessible for the said reasons that I just explained, right? While region 2 is accessible to the particle. Now, this was purely classical. And one way you could think about this is, let's say there's a hill over here, and you're standing over here, and there's a ball, and you kick this ball. If you cannot give it enough energy that is over here, that is required to overcome this potential that exists over here, then the ball, if you kick it and it does not have that enough energy then the ball would always go up this hill and it would come back down. However, if you give it enough energy E, then what happens is it would cross what this thing is called as a turning point. It would cross this turning point and it would go on this other side of the hill, right? But quantum mechanically, what can happen is, if this were a quantum mechanical particle and there was a hill over here, what can happen is it can tunnel right through this hill and reach at this point. So this is quantum mechanically possible, and in fact, this quantum mechanical tunneling is the reason for radioactive decay. And another, well, a very good example is uh, why the sun shines. The sun basically shines because of this quantum tunneling effects. If quantum tunneling was not possible, life would not exist.